All right, welcome back to Étale cohomology on November 3rd, 2020. Hopefully I can make this lecture entertaining enough to distract you guys from current goings on. So last time we talked about Kunith and cycle class maps. So today, I want to talk a little bit about Chern classes of vector bundles. And Poincaré duality. All right, so let me briefly indicate what Chern classes are. So what is a Chern class? And then I'll say a word about the construction. I'm not going to give too many details. So what are Chern classes? So given a vector bundle, so here X is going to be smooth and projective over a field. Okay, and so given, I'll explain. I mean, we won't need that for everything. I'll say, but and in particular, the definition of Chern classes doesn't require it, but under a lot of the properties do. So I'll indicate where we actually use it. So given a vector bundle E on X, there are the goal will be to construct classes, so Chern classes Ci of E. So in singular cohomology, you generally think of these as living in just H2I of X with coefficients in Z. And there's a twist to take care of here, just like in cycle class maps. So where these live, they live in H2I of X with coefficients in ZL of I. And here, as usual, L is prime to the characteristic of K. Okay, so we've already seen one of these. So example. So for I equals 1, we want C1 of E to live in H2 of X with coefficients in ZL of 1. So does anyone know how to make a class, such a class associated to a vector bundle? Any thoughts? Well, let me just remind you. So ZL of 1 is the ZL sheaf corresponding to the sort of diagram mu L to the n. So you can think of it as kind of the inverse limit of mu L to the n's. And there's a short exact sequence, 1 to mu L to the n to GM to GM, which gives rise to a Kummer map. So this is the boundary map from H1 of X with coefficients in GM, also known as pic X. And let me call this boundary map kappa for Kummer to H2 of X with coefficients in mu L to the n. Here this is L powers, L to the nth powers. And these maps are compatible, so I guess I should call this KL to the n. So gluing all these maps together, one gets a map which I'll call kappa also, from pic X to H2 of X ZL of 1, which remember is the inverse limit of all of these groups. So the definition of C1 is it's just kappa applied to the determinant line bundle of V. So the top exterior power. Okay, and then the theorem, which I'm not going to prove, but I'll say a word about the proof, is that there exists a unique assignment E goes to Ci of E, satisfying the following three properties. So one, it's functorial under pullbacks. So what that means is that f star of Ci of E is the same as Ci of f star of E. So two, C1 is defined as above. So C1 is kappa, sorry, C1 of E is kappa of the determinant of E. Sorry, let me turn off my notifications. And three, so it's multiplicative under exact sequences. So let me explain what I mean by this. This is the most complicated one. So if we define C of E to be one, sorry, yeah, 1 plus C1 of E plus all the way up to C, well, let me just write it as an a priori infinite sum. So where does this live? So this lives inside of the direct sum of H2I of X with coefficients in ZL of I. So if we write it as this direct sum, as this element of the direct sum, then if we have a short exact sequence 1 to E1 to E to E2, sorry, I don't know why I'm using ones here. I would say the identity section to a vector bundle should probably be denoted 0. Then what do you get? Then we get that C of E, the so-called total Chern class of E, is given by C of E1 times C of E2, where here this dot means the cut product. Okay, so these are the three defining conditions of the Chern classes. Are there any questions about this theorem? All right, so what's the proof idea? I'm not going to say very much about it because the proof idea is like exactly the same as the proof in topology, but the idea is to analyze the cohomology of the projectivization of E, from which the Chern classes can be extracted. Can be extracted. So meaning from the cut product on the cohomology of the projectivization. So one uses that to make a construction, a construction of these CIs, and then uniqueness is purely formal. So what do you do? Well, you figure out what happens. Well, we know what happens for C1, so we know what happens for line bundles. So if you could write every vector bundle as something with let's say which has something with a line bundle as a quotient and a lower dimensional vector bundle as a sub, would be done by induction on dimension. And there's a number of ways to do that. So for example, if you're on a projective variety, you can just well, you would need to control tensor product. So the easiest thing to do maybe is we'll pass to a flag, like the sort of, well, you can even just pass to the projectivization of E. So there E has a line bundle quotient. The pullback of E has a line bundle quotient. And then one has to argue that saying what the Chern classes are on the projectivization determines them on the base, but that follows, for example, by analyzing the map on Étale cohomology from the cohomology of the base to the cohomology of the projectivization. So this is the construction, and then let me maybe briefly write. So uniqueness. So you use induction on the rank. On rank, and then if pi is the map from the projectivization of E to X, then pi star E has a line bundle quotient with lower, and then the kernel is lower dimensional. So that means that the total Chern class of pi star E is 1 plus C1 of this O of 1 times the total Chern class of the kernel. So these, we know what they are by induction, and then the claim, which I'm not going to prove, is that the map from the pullback map pi star from the cohomology of X to the cohomology of the projectivization of E is injective. So knowing what the Chern classes are on the projectivization, which we know by induction in this formula, tells us what they are on X. All right, so that's the idea of the construction. Are there any questions about that? Okay, so I wanna make some remarks about this because it in principle will show up for us, although I'm going to punt a lot of the ways it does show up for us. So the remark is that this multiplicativity in short exact sequences means that we actually get a map from the K group of X to so here this is, if you like, this total Chern class to this direct sum of cohomology groups. Sorry, this should be the direct sum over I to I of coefficients in ZL of I. So we get a map like this. This is just a map of sets, or it's really a multiplicative map. So what is this K group? So here K star of X is the free abelian group on isomorphism classes of vector bundles on X modulo the relation that E is equal to E1 plus E2 if there's a short exact sequence 0 to E1 to E to E2 to 0. Great. So here I've made a group for you, and I've said that there's a multiplicative map. So what does that mean? It means that if you take the sum of two things here, it goes to the product over here. So it's some kind of like exponential type map. Okay, so what's the relevance of this? So maybe what I want to explain is how to understand, like how to relate this to the cycle class map we defined last time. And I think this is like a really important thing to know, which unfortunately, like we don't have time for me to prove the growth and decrease Rock theorem. So a lot of what I'm going to say I can't prove in this course, but I want you guys to know about it, and we'll use some of this information later on. So one can modify this. So one can modify to get actually a ring homomorphism. Which I'll call ch from k star of x to this direct sum over I of h2i of x CL of I. So here, what is the product structure? So here on the left, this is a ring with the cup product. And here, this becomes a ring with the tensor product as the operation. So I'm not going to give you the details. More or less, the idea is to take kind of the log of this homomorphism, but the actual details are a little involved. The easiest thing to say is for the class of a line bundle, what you do is you take kind of the exponential of the first Chern class of that line bundle, so like 1 plus C1 squared over 2 plus C1 cubed over 3 and so on. And then to define things for general vector bundles, you can, for example, pass to the flag variety, or you have a filtration by line bundles, and then use the formula for line bundles there. So that technique is called the splitting principle, if you've heard about that before. Okay, so what's the relevance to this thing? So maybe I shouldn't call this ch, because something else is often called ch. Let me call this a gamma. So the relevance of this is that we can reinterpret the cycle class map we had from before in terms of this gamma. So there's a natural map. The reason I renamed gamma is that there's a natural map ch from what I call the C star of x. So these are the Chow groups. So these are cycles modulo rational equivalents. So this maps to k star of x tensored with q, and sorry, this should have been a ql before. And this maps to the direct sum of h2i x ql of I, be this map gamma. And the composition, so the composition is precisely the cycle class map from before. So what that shows is, if you believe this fact, which is highly non-obvious, is it shows that this cycle class map is actually a ring homomorphism. So meaning you can compute, for example, intersection products in Chow groups in terms of cut products in analytic cohomology. And then the really amazing thing is that in fact, for X smooth and projective, so ch induces an isomorphism between the rational Chow groups of X and the K theory of X. So in fact, from the point of view of cycle theory, you can more or less forget about this group as long as you're willing to work rationally. And so this was kind of Grothendieck's point of view on Chow groups and intersection theory, was to actually kind of forget about honest cycles and just work with this rational group of vector bundles. And there are good reasons not to do that. Like in particular, this is much more geometric. So like if you have two physical varieties which are intersecting nicely, then computing their intersection product here is very easy, whereas computing it here is quite involved. Like you have to come up with some kind of resolution of their structure sheaf of their ideal sheaves by like locally free sheaves, and then take the tensor product of some complexes and blah 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 blah. But I did want to mention that somehow for sort of purely formal things, so things which don't involve honest computation, this group is just as good, which this group is just defined in terms of vector bundles. So the proof of this is somehow part of the Grothendieck-Riemann-Roch theorem. Yeah. So maybe let me make just a couple remarks about how one proves some of these things. I mean, so a big chunk of this is just redoing growth in Kruman-Rock with this group kind of replacing this one. So for example, to check that this composition is equal to the cycle class map from before. Yeah, one way to do this is to do it to work this out for excuse me. Yeah, well, maybe let me not give too many details about that. But yeah, so this is sort of what I wanted to say about Chern classes. Sorry, that was a little bit awkward. Are there any questions about that?
I guess I'm a little bit confused because in the literature, I think there's the Chern map comes from the Grothendieck group to the Cho group. Is that right?
Oh, I'm sorry.
I mean, for Landbound, you indulge.
Oh, I'm so sorry. Yeah, you're absolutely right. Yeah, sorry. Yeah, sorry. Ugh. I mean, it's an isomorph. Yeah, I guess you're right, yes. But it's an isomorphism rationally. So maybe if I do this, this is the easiest thing to say. Yeah, sorry about that. Yeah. Oh my God. Sorry. You might be able to tell I haven't gotten much sleep last night. Yeah, you're right. So let me call this maybe inverse. Maybe call this Q an invert. Sure, that's probably the easiest thing to do. Yeah. But yeah, what I should have written is the map goes the other way. So you go from K3 to Chow, and then this composition, this gamma we wrote is the same as going from K3 to Chow, and then Chow to cohomology via the cycle class map from before. Very sorry about that. That was a good point, Peter. Yeah. Are there any questions? Other questions? Yeah, I'm very sorry about that. All right, so if not, let me talk about Poincaré duality a bit. Yeah. So okay, so what's the theorem? So here X is going to be smooth over a separately closed field. And lambda is going to be Z mod MZ, the constant sheaf Z mod MZ, where here M is invertible in K. And then the theorem is as follows. So this is just an analog of Poincaré duality for manifolds, which I'll recall briefly. Well, there's a cup product pairing from the cohomology of X with coefficients in lambda times the cohomology in degree 2 dim X minus I compactly supported with coefficients in lambda twisted by D. So just a reminder, so what is this? This is lambda tensored with mu m to the tensor D. And then the cup product maps this to H 2 dim X compactly supported with coefficients in X Étale lambda of D. So maybe before I finish stating the theorem, just a remark. So why is this where the cup product maps to? Well, how do you compute these things? So you would push forward lambda. Yeah. So to compute this thing on the right, you take a compactification of X and you take the extension of lambda D by 0 to the compactification. To compute this thing, you would take the derived push forward of lambda to the compactification and then use the Lauré spectral sequence. But when you and then you would get so when you cup those two things together, you'd get something in this extension by 0 tensored with derived tensor product with this. But that's at least in degree, yeah, in the relevant degree. So in degree 0, that's just going to be again the extension by 0 because like on X itself, this is the derived push forward of this to compactification is just lambda. So that's why the target is here. So then the Poincaré duality has two parts. So first of all, the claim is that there's a canonical isomorphism between this and just Z mod MZ called the trace map. So this is an isomorphism. Here, sorry, smooth, it should be a smooth variety. So what I need about varieties is I need, this is connected. So the claim is that we have an isomorphism like this, and then moreover, under this isomorphism, there exists this canonical map trace, this canonical isomorphism, and then also this, and then under this isomorphism, this cut product becomes a perfect pairing. Okay, so what's the analogy in topology? So suppose, sorry about that. So the analogy in topology is, so suppose X is a oriented manifold. Then there's a map from H dim X, X R. Well, if we just think of this as Theorem cohomology, so what is this? This is given by top forms on X, and we have a choice of orientation. So that's an element of that's a top form, and then there's an integration map to R. So this is the trace map. And then what is the cut product? So given HIXR times H dim X minus I XR. Sorry, this should be compactly supported. You can only integrate a compactly supported form to H dim X C XR. So what is this cut product? So given a form omega and a compactly supported eta, we just wedge them together. And that gives us a compactly supported top form. Okay, so this is the analogous situation in topology. And hopefully you've all seen the fact that this is a perfect pairing. If not, that's okay. I mean, logically, these things are independent. So the interesting things to notice is that when we have this twist here, there's actually a kind of canonical orientation. So this is analogous to the fact that complex manifolds are canonically oriented. Right. So like, for example, on a Riemann surface, you have DZ wedge DZ bar. That's a canonical orientation. Yeah, so this lambda D here, so this twist is a little bit maybe surprising, and it's also there in the complex setting, but it's sort of there in a subtle way. So yeah, I think I could talk about that if someone would like to hear about it, but it's a little subtle, so maybe let me skip it if not. Yeah. Okay, so I want to explain at least the idea of the proof of this. So again, it's one of these things that's extremely involved, and we don't have time to do details. So the proof, just like the statement, has two parts. So one will be the construction of this map trace, which, let me remind you, was a canonical isomorphism between H2I, H2 dim X X lambda of D and Z mod MC. And then two is so checking that the cut product is a perfect pairing. So checking that we have a perfect pairing. And in doing the latter, we'll actually dramatically kind of generalize the statement. So we'll discuss at least a little bit of Verdier duality. Okay, so let's start by the construction of this trace map. And maybe let me remark, so Tony Feng has some really nice notes on this. If you Google like Tony Feng, Poincaré duality, and Étale cohomology, it'll come up, are a very good reference. There's a few typos, but it's quite nice. And I used that reference to prepare this lecture. Okay, so I'm actually going to approve a more general statement. So more general claim. So there's going to be a canonical map. So well, let me do the setup here. So suppose f from X to S is a smooth compactifiable morphism with geometrically connected fibers. So remember, compactifiable meant that there was a X prime, so that we could factor the map X to S as a map from X to S and X prime to S, where X to X prime is an open embedding and X prime to S is proper. So then what we want to do, so what are we going to do? So the claim is that there exists a canonical map called trace, which goes from R2D, I'll say what D is in a second, F lower streak of F upper star of F twisted by D to F. So here D is the relative dimension of F, and I should have assumed that F has pure dimension D. Oh, I said geometrically connected fibers and smooth, so I guess it's actually okay. Yeah. So D is the relative dimension of F here. Okay, so let me briefly remind you. So what was this R2D of F lower shriek? So what this was is you choose a compactification of the morphism F, and then there's a functor given by composing F lower star with the extension of F by 0 to the compactification. And so our R2D of F lower shriek is it's not quite the derived functors of that. So what it is it's so let me just recall briefly what the derived what Ri of F lower shriek is. So here if iota here from X to X prime, and then we have some F twiddle. So if this is a compactification of F, then we just defined Ri F lower shriek of a sheaf G to be Ri F twiddle lower star of iota lower shriek of G. Okay, so that's what this term means. So we're gonna construct this claim, and we're gonna construct this map, and moreover, it's gonna satisfy a bunch of properties. So first of all, so for curves, we've actually essentially already constructed this. So for curves over a separably closed field, so this was implicit. So this agrees with the computation we did earlier. So what do I mean by that? So what I mean is that we've already computed, for example, the compactly supported cohomology of mu n on a curve, and if we have a curve over a point, everything is more or less mu n, right? So any possible f. So we've already constructed a sort of canonical like map like this for curves if f is mu n over a point. So 2, this is functorial in F. So 3, it's compatible with base change. So what does that mean? It means that if I have X to S and then an S prime mapping to S, and I form the Cartesian square, then if you start with a sheaf on S, pull back and do this on X prime, it's the same map you get if you make it if you take the map on S and then just pull it back to S prime. So if F is Étale, then then D is 0, right? So we want to map F lower shriek, F upper star of capital F to F, and this is just the counit of the adjunction. So it's the counit of the adjunction between F lower shriek and F upper star. And finally, we want this map to be compatible with compositions. So meaning if you have X to Y to Z, you can form this map relative to the map Y to Z and X to Y. And there's a diagram which you should try to write as an exercise explaining how these maps are compatible with each other. Okay, and then the theorem is that there's a unique functorial map like this, like satisfying. This is a natural transformation, right? So there's a unique natural transformation satisfying all these conditions. Okay, so let me say a word about the proof. So proof sketch. So suppose we're in the following situation. So suppose we have X to affine space over S to S, where this is just the projection and this is Étale. So every smooth morphism locally looks like this, right? This is the structure sheaf for the structure theorem. Sorry, not the structure sheaf. The structure theorem for Étale morphisms. So so compatibility with composition. So I'm going to first make a construction and then I'll say a word about why it's independent of choices. Sorry, Bob asked if X over S is supposed to be smooth as well as proper. So X is smooth but not proper necessarily. So it's smooth and compactifiable. So here this is the condition. And I see you were asking about X prime here. So this map F tilde need not be smooth. Yeah. Thanks. Yeah, sorry about that. Yeah, in general, I mean, we can't guarantee something like that. So even if S was a point, so if S was a point, this would be like asking for resolution of singularities, which we don't have in general. Yeah. Great. So here compatibility with compositions tells us it's enough to do, so let me call this map G, tells us that it's enough to define the trace map for G and pi. So for G, we already said what it is. It's the counit of the adjunction. Between G lower shriek and G upper star. So here, this is because it's an Étale morphism. And now for pi, so for pi, there's a little bit of subtlety. So what one needs to do is one needs to do the computation we did for curves over a base. So we computed the compactly supported cohomology, for example, of A1 before, but we didn't do it over a base. So what you do is you factor this as this maps to n minus 1s, which maps to a n minus 2s, and so on. So these are all relative curves. So for pi, we can factor into a sequence of relative curves. and then use the curve case. And in fact, it would not be so hard to do this from what we've already done. So for example, excuse me. So for example, you could just argue that in this particular situation where you have an AN bundle over a base, cohomology computes with base change. Sorry, cohomology with coefficients in a sheaf whose order is prime to the characteristic commutes with base change. So in particular, if you want to compute the push forward of the constant sheaf, for example, from A1S to S, you can compute that over a point and then base change to S.
Excuse me, I don't remember what the co-unit of a junction between G lower streak and G upper streak is, or any of those.
G upper star. I see. So at least when we define G lower shriek, so I think I defined that for an Étale morphism. So at least I claimed that it was left adjoint to G upper star. And this is not totally obvious, but let's see if we can just say what the map is. Yeah, I don't think it's so bad. So let's discuss this co-unit of the adjunction. So here, so G from X to Y is an Étale morphism. So the claim is that there's a map from G lower shriek of G upper star F to F, so a natural map. So can anyone tell me what it is? Yeah, sorry. So there's two possibilities. So one, so here we need to define this. So for U contained in Y, we want a map. We want to map G lower shriek of G upper star of G lower shriek of G upper star of F of U to F of U. So how do we compute this thing? So one way to do it is we can just compactify. So this is proper. This is open. Excuse me. Sorry, I'm yeah. So in this situation, so let's call this pi. So what is G lower shriek? So G lower shriek is just pi lower star of iota lower shriek. So yeah. So I claim there's we can do, yes, we can break this into two steps. So one is sorry, I should have thought this through first. Yeah, so it's enough to show, in fact, that that pi lower star and pi upper star are adjoint in this case. So this is sort of the reverse of the usual junction, right? So one has to check this in the proper case, and then two, we need that iota lower shriek is adjoint to iota upper star. So maybe let me do two. So here two, this is the case, so proof of two. So this is the case of an open embedding. So in this case, we now want iota lower shriek of iota star over upper star of F of U maps to F of U. And there are two cases. So case one is that U is contained in the image of iota. And in this case, we can just take the map to be the identity. So this is trace. And in the other case, if U is not contained in the image of iota, then this group iota lower shriek of iota upper star F of U is just 0. So we can take the trace map just to be the 0 map. Yeah. So then there's something a little bit tricky. So in this proper case, what do we do? So let me think for a minute to see if there's something easy to say. Yeah. So what do we do in the proper case? Okay, yeah. So in the proper case, I think we can do it too. Sorry. So let's do 1. So in the case, so now we want to show that, so we want to map from pi lower star of pi upper star of f to f. So the claim is that in fact we can do this after, so after pull back through pi. So that we get a map pi upper star. We want a map pi upper star or pi lower star or pi upper star of f to pi upper star of f. So where does this come from? So this comes from this adjointness. So for this from the adjointness, from the usual adjointness of pi upper star and pi lower star. And now the claim is that this map actually descends. So this exists from the usual adjointness of pi upper star and pi lower star. So the claim is that this adjointness descends. Sorry, this map descends. To a map pi upper star, pi lower star, pi upper star of f to f. And so why is that? Sorry, I'm blanking a little bit here. Maybe I need to assume something. Yeah, maybe let me get back to you on this, Bob. Sorry about that. I'm blanking a little bit here.
Again, I feel really foolish asking this, but to me, the words counit of a junction themselves are kind of meaningless. I don't know.
Oh, I see. That I can definitely explain. Oh yeah. So suppose you have a map. So suppose what does it mean to have counit of a junction? So suppose you have two functors, f from category C to D, and G going the other way. So here here f is left adjoint to G. So then I claim that there's always a natural map from FG of any object X to X. So here X, I guess, is an object of D, right? So what is it? Well, what you do is you take hom of GX to GX. So this is in C. There's the identity element in here. So this is id of GX, right? But this set is canonically isomorphic just by the definition of a junction to hom in D of FG X, right? So all I did is I moved this G from right to left using the definition of what it means to be a left adjoint.
Okay, thanks.
Yeah, so the identity map maps to this what I'll call eta, which is called the co-unit of the adjunction. Yeah, and then there's also, so there's also a map from X to GF of X, which is called the unit of the adjunction, which you just construct the exact same way, but you move F from left to right rather than moving G from right to left. Yeah, sorry about that.
Okay, thanks.
Yeah. All right, so I'll get back to you on this. Sorry, I think this is something that I meant to do earlier in the class, and maybe I forgot to do it. And I'm having trouble reconstructing it off the top of my head. Oops. All right. Sorry. So that was so I claim that was a construction of a trace map modulo this detail in the case where we have a map that looks like it comes from the local structure theorem for Étale morphisms. It's not at all obvious that it satisfies any of the conditions, or that it doesn't depend on the choices we made here. So the claim though is that we can at least reduce the construction to this case So how can we do this? Well, just by Meyer via torus. So a smooth morphism locally just looks like the case above. And then the claim is that one can build a sort of global trace map if one has one locally. Okay, so then the once one does that, there's still a lot of non-trivial work to do. So one still needs to understand the extent to which this map is well defined and also unique. Like so why is there a unique map which satisfies the given properties? Well, uniqueness is not so bad. So uniqueness, our construction earlier was forced by the axioms. So the construction for so-called standard Étale maps was just forced by the axioms. So the hard part is well-definedness. So there are two choices we made when we described this trace map earlier. So one of them is excuse me. So one of them was the choice of an open set. And the other one was the choice of Étale map. So here, well, let's take our open set U. And the other one was a choice of Étale map from U to affine space over the base. So a priori, if you take an open which admits a factorization into a standard Étale morphism, it couldn't admit many, right? So the choice of open set is not so bad. So I'll just say a word about what you do. I mean, actually writing this out again is very involved, as with all of these things. So for the choice of open set U, so given 2, you can choose a cover. So you take common refinements. And then argue that some natural diagram commutes. And for choice of 2, so in 2, what you end up with is you end up with the following situation. So let's just think about the case where you have a relative curve, and we factored everything into relative curves. So this is the key case. So suppose you have 2 maps like this, where this is Étale, and these are both the structure maps to S. So one needs to check that the map one gets doesn't depend on this choice of Étale map. But this is just the case of curves, which we made a really canonical map earlier when we computed the compactly supported Étale cohomology of curves. So this isn't so bad. So really this well-definedness is not actually so bad. So the construction of this map is not so bad. And now the claim, finally, the last claim involved in the trace map is that if x to s, so we've constructed this map in general, right? So we've constructed a map from R, meaning in general, when we have a smooth morphism a smooth morphism of pure dimension D. But so now the claim is that if x to s has geometrically connected fibers, this map from R 2D F lower shriek of F upper star of F twisted by D to F is actually an isomorphism. And again, so I'll just give you a proof sketch. So one is in the case where this is a relative curve. You can check on stalks. And then it boils down to the computation for curves we already did. And then two is you reduce to this case. Via, again, it's the structure theorem for Étale morphisms. So there's a little bit of subtlety in the reduction, which is that that when you take this, up here, this map doesn't have geometrically connected fibers. So one needs to think about not this map and this map separately, but actually you factor this map as a relative curve, and then you study these maps, and you have to argue that they have geometrically connected fibers. So this is not a totally trivial reduction. Great. So we have 1 minute left, so maybe I should stop. Are there any questions? All right, well, I'm going to stop recording and stick around for a while in case anyone has any questions. And I'll see you guys on Thursday when hopefully things will calm down a bit.